The expressions that you're seeing in that left-hand column are actually all expressions that are completely factored or in a factored form, since it's just the product actually of a factor with itself. So we know that whenever you multiply something with itself, right, then it's really kind of squaring that expression. So actually all of these here we typically will refer to as the squares of a particular binomial, since what we are multiplying together with one another are two-term expressions there. So I want to expand these out into their expanded forms so that we can pick apart some of the relationships we see in the expanded forms. That helps us bring some insight in terms of like what we might want to recognize as we're factoring these sorts of expressions. So with the first example right here, we've got x plus 5, that quantity is squared. So we know that the only way to multiply this out is to write out that base that many times, and then that result means that we have to FOIL this expression ultimately. So when we do FOIL that, you're going to have the x squared, and then plus 5x, and plus 5x will combine to be plus 10x, and then 5 times 5 is going to be plus 25. And then I want to jump to the 5x minus 2, that quantity squared. So if we write that out separately first, and then we do the FOILing of that, then 5x times 5x is going to give you 25x squared, and then minus 10x, but then another minus 10x means you get a negative 20x term there, and then negative 2 times negative 2 is then plus 4 that we get out of there. Okay, so I think that's enough in terms of just examples with numbers and variables. So if we just generalize exactly what we were seeing right there, if we ever have just anything a plus another anything b, and then we multiply it with the same sort of binomial, so a plus b, then what we're going to get out of that when we FOIL that is we're going to get a times a, so we're really going to get that a squared, and then we're going to get a times b, but then this is b times a, but b times a is the same thing as a times b by commutativity of multiplication. So we're able to combine those terms together, and what you actually get is you get 2 times a times b. That will create that middle term there, and then finally you'll have b times b at the end there, which will then give you a b squared term that you see at the conclusion. And so you'll see how, like in the example of maybe that expression right there, how really you do get something of the form a squared plus 2ab plus b squared, because if you recognize the fact that this right here is, if you treat that as like your a, and then you treat this right here as your b, and then you can see that, okay, yep, the next binomial also has the a and the b, then of course this right here is really your a squared, because it is, right, 5x times 5x. And then the term that you see right here, this negative 20x, is really coming from taking 2 times your a times your b, because it really is taking 2 times the a, which is 5x, times the negative 2, and 2 times 5x times negative 2 does equal negative 20x. And then finally at the end of that result, so right here, this 4, that is the result of your b squared, because if your b was a negative 2, negative 2 squared is a positive 4. And so that's the sort of relationships that we're seeing with the result of the square of a binomial. So what we call these sorts of expressions that are always going to be able to form like a squared plus 2ab plus b squared is we actually denote these as perfect squares, because they are the result of taking the same thing times the same thing, right? Every single one of these is, so they're perfect squares, and since they end up having 3 terms, we may also call them perfect square trinomials. I do just want to note that if there's a minus going on right here, then basically you get the same thing. It's just that the middle term is going to be subtracted, but the other 2 terms are still going to be positive if you have something kind of that form. So some things to kind of recognize with perfect squares is then, because you're doing a lot of multiplying of the same thing with the same thing, you're going to notice that like the beginning term and the end term always have like perfect squares kind of involved, like the 1s and 4s and 25s and that sort of thing. So that can be kind of helpful to recognize as you're factoring expressions like this. So taking a look at some examples right here, it does say to factor each perfect square trinomial, so that kind of clues you in. So like with this first example right here, you have x squared minus 16x plus 64. So there isn't a GCF, so we don't have to worry about that, which is great. And then you have to think about, okay, so what's going to multiply to be a positive 64 but have a negative middle? So obviously minus minus. You think about the options that can multiply to 64, like you do 8 times 8, and actually that's what we would kind of want, right? Because then you would have minus 8x and minus 8x in the foiling there that would add to the negative 16x in the middle. So that would be the factored form, and if you left it like that, that's totally fine, but we know that in math, if you do ever write like something times the same thing, you could simplify that by using an exponent. And so writing this as the quantity of x minus 8 squared would be a much simpler way to be able to write that out there in particular. And then I'm just going to skip the middle example. I'll just give you the answer to it. It's 5x plus 2, that quantity squared. And then jumping into the last example, you can see there's like a 49 at the beginning and a 144 at the end, and they're both perfect squares, right? So that might help you to think, okay, well, maybe I could do 7x times 7x to give me the 49, and then, I don't know, does like 12 times 12 give me 144? Of course, but what really matters, of course, is we want to get the negative 168 in the middle as well. Clearly, if that's a plus and that's a minus, then both of these would need to be minuses. So we would get out of the outside negative 84x and then another negative 84x, and that does combine to be negative 168. So this does turn out to be the factored form. Then, of course, because they're the same factors, you could kind of simplify that down to just the square of the quantity of 7x minus 12 there. Some things you really want to be careful about is, like, just because there's a perfect square at the beginning and a perfect square at the end does not mean that it's necessarily going to be a perfect square trinomial. So like with the very first one right here, you see 9x and 9x squared and then the 1, so that might help you to think like, okay, maybe it's 1 times 1 and then like 3x times 3x, right? And then everything's all positive, so you can do 3x plus 1 and 3x plus 1, right? But if you FOIL that out and you look at particularly at the outside and the inside, you get plus 3x and plus 3x, so out of that you should have a 6x in the middle, but we wanted it to have a 10x, right? So it turns out that it doesn't factor as 3x plus 1 times 3x plus 1. So that tells you then that 9x squared plus 10x plus 1 is not a perfect square trinomial, so you'd have to think about like other ways you would factor it. It does turn out with this one that it is 9x plus 1 times 1x plus 1, which is then clearly the product of two different quantities right there, so you just kind of have to leave it like that. Same thing kind of happens with that particular example. So you just got to be careful and think really through your factoring fully.